All right. Good afternoon, everyone. We're very pleased to welcome Dr. Eric Isaacs today from the Argonne National Laboratory. He's joining us for a Green at Google presentation on energy policy and the latest breakthroughs in research to come out of Argonne Lab. And in case you're not familiar, which all of us probably are given our technical backgrounds, but Argonne is one of the world's foremost centers of physics and materials research and also home of famous white deer. Dr. Isaacs is a professor of physics at the University of Chicago, and he comes from storied careers at both Bell Labs and the Center for Nanoscale Materials at Argonne. And so he's going to review for us today some of the basic scientific research and the game-changing energy breakthroughs that are happening right now at Argonne, with the goal of finding revolutions in the energy sector. Whether that's through thorium or the batteries for the Chevy Volts, I'll leave that to Eric to paint the picture. And we'll have time for some question and answer at the end for the use of the Q&A mic. But without further ado, please join me in welcoming Dr. Isaacs to Google.
Thank you. Thank you, Cliff. I want to thank Cliff for arranging this opportunity for me. So I would like to talk about energy, as Cliff said, but in the context of really what it takes to, let's call it, change the game. Something that, of course, Google has done in many ways, and certainly the automobile has done it, changed the game in the US. So I'd like to talk a little bit what game-changing means, and of course you'll see my natural tendency is to come out as a materials physicist, condensed matter physicist, and talk a little bit about the cool stuff behind the technology. So I thought I'd start with an analogy, which is, of course, football. Whether or not you knew it, I didn't know this until a few days ago. Football wasn't originally prolate. It was actually originally spherical. And the game was invented effectively so that college men could get out and practice sportsmanship, team building. They could practice essentially military-like activity without getting too badly hurt, without getting shot at. It turns out that, of course, they also got brutalized quite a bit. But there were real game changers. And when I say game changer here, by the way, I don't mean winning a game like we see at Stanford University. I mean really changing the game. What changed the game in football was going from spherical to prolate. And all of a sudden it went from a game which was kind of slow, maybe a little violent, to one that was extremely fast and probably very violent. And in fact, it got so violent that in 1905, 18 players, college players, died. And it caused a few years later, President Teddy Roosevelt to come out and say either change the game or stop playing it. And the point of saying that is there's sort of a technological change from a spherical ball to a prolate ball, which really did change the game. But also there was political intervention. And when we talk about energy, you can't talk about one without the other. And you can ask me later what's more important, politics or let's call it strategy versus technology. And of course, in the end, the real change in the game was now it's a multi-billion-dollar industry for the colleges. It's a multi-billion-dollar industry in general. It's no longer just a game for a bunch of hacks to play in a field somewhere in the back of the school. It's really a serious sport. So that's one analogy for what change is. Let me tell you a little bit about one that's a little closer to my heart, which is change in technology. Many of you will recognize this. This is just a charged couple device. It's one that, this one is a reasonably recent one. Just the story of how this changed the game. This is two guys who actually 2 years ago won the Nobel Prize. Unfortunately, the guy on the right here, George Smith, just died. But Smith and Boyle were working really as individual researchers in a lab at Bell Laboratories. And they came up with an idea for memory. And at the time, they were competing against something you guys may remember. Some of you here may remember bubble memory. And there was a decision made at Bell Labs to cut this program, which was to make it solid-state memory instead of bubble memory. And these guys figured, what the hell else can we do with this stuff if we're not going to make a shift register and a memory go with it? And they ended up deciding, hey, we have an idea. We can use the optical properties of the material and make it into a camera, make it into something that could image. And they did. And they actually saved their funding to do that. This is just an example of the first device, and it's a cool device. It is a shift register, basically, but it's what's behind the charge couple device that's the silicon. And here's the first image, just to give you a sense of what it looked like. What's really important, though, in the story about changing the game is that it did start off as this really PI kind of program, a couple of guys in a laboratory. But very quickly, who adopted it first? It wasn't a big product at first. It wasn't in your iPhone at first, of course. It was actually adopted by the military. It was first adopted for spy satellites. In fact, this was invented in 1969. By 1974, this device was orbiting the Earth and taking images of places like Afghanistan, places we still want to take images of. This, of course, I just retrieved yesterday off Google, and this is, you guys know this place very well. But any of us now can use these charge-coupled devices in space and, of course, on your body. You have it in your telephone. So that I'd call game-changing. There actually were two early adopters. One was the military to do this kind of satellite imaging down to the meter now. But there was also, of course, the astrophysicists. So there were scientists still in the game, even in the mid-70s, realizing very quickly that it wasn't, no longer did you need film, you could do some stuff much more clever by using charge-coupled devices. So the point here is that there was a big game, it was changed. And it was changed by two guys at first who didn't know they were going to change the game. It was really just two people who ended up starting that revolution. But it also took many years, 5, 6, 7, 10, 15 years to really ultimately change the way all of us live our lives. So changing the game can take a long time. And so now I want to talk about, in that context, energy technologies and thinking about how are we going to change the game with energy technologies. Just, simple fact is today still we rely almost entirely on fossil fuels. Solar energy, which we all love to talk about, I know you guys have a solar automobile, is still less than 0.1% of the energy production in this country or anywhere in the world. So it's still a long ways from being game-changing. It's exciting to talk about, but it ain't game-changing yet. So, of course, the challenge is obvious. This is another nice image taken from the sky, taken of Earth. It's of course, a time sequence picture. And really the point of showing this is two reasons to show it. One is just to say that we're using a tremendous amount of energy on the face of the Earth. The electricity associated with this, just the electricity alone, is about 15 terawatts. The US consumes about a quarter of that, maybe a little more than a quarter of that. And you can see also a lot of dark regions, which are soon to be developed. So the growth, not only do we consume a lot today, but by 2050, we're looking at probably roughly a doubling of the consumption in electricity. So there's huge growth. And of course, that's electricity, which today across the world is mostly generated by fossil fuels. So that means that we're also producing carbon. And many of you have seen diagrams like this, a famous wedge diagram. Today, we're spewing about 30 gigatons of carbon into the atmosphere. What does that mean? 30 gigatons. Naturally occurring carbon in the atmosphere is about 700 gigatons. So it's about 5% a year. So in 20 years, we're doubling the amount of carbon, unless it's absorbed or unless the Earth is adapting. So we don't know what's going to happen. This is a chart that's the International Energy Agency, where they project out based on current conditions. So business as usual, and you can see that essentially there's growth in the carbon production, roughly speaking, with the growth of electricity consumption, because there's a direct correlation between the carbon we produce. What's interesting about this is the IEA also suggested that there are ways that we could start thinking about bringing this curve down. Business as usual, I would argue, is unacceptable, but one could argue that there's a lot of things you can do. And the first and easiest thing is energy efficiency. It doesn't sound very glamorous, very sexy, but even in this country, over half of the energy we use is wasted as heat. So these lights that you have here are probably a little more efficient than most, but electricity is used, 20% of electricity in this country is used for light bulbs and lighting. And of that, more than half of it is wasted simply as heat. So there's a lot of waste. So if you can imagine solid state lighting, et cetera, which you'll hear about, you do a tremendous amount just in suppressing the amount of carbon we produce. And there's other things here, renewables, and I'll focus on a few of these as we go forward. Just as a summary, there are many things, and you guys are all familiar with the types of alternative energies here. Wind, solar. Again, solar is a tiny piece of what we produce today. Wind's a little bit larger than solar. It's a few percent, but not much larger. We, of course, still have nuclear. In this country, 20% of our electricity is still nuclear. There's 104 power plants. They're getting older. What are we going to do with those? And of course, if you're going to do things like biofuels or continue to use fossil fuels, thinking about carbon sequestration is critical. But one of my main points here is that every one of these is not a done deal yet. None of these are major adoption, except for nuclear. None of these have been adopted in a major way into our energy system. And the question is, how do we help drive that? What makes the game change with any of these alternative technologies? We talk about them, we'd love to see them happen, but they're far away from happening yet. So one of the places where we're thinking a lot about this, and Cliff introduced me as being the director of Argonne National Labs, is at the National Labs. So I thought I would just tell you, I'm not going to spend a lot of time talking about National Labs, but I just want to tell you how we're different from academia and how we're different from industry and what we do. We're very academic in the kind of research we do, but there's a huge difference in the kind of research we do. It's mission-driven. So it looks a lot more like a Google or like an AT&T doing Bell Labs or like an IBM doing Yorktown Heights. Doing research, fundamental research, but with the idea that maybe not tomorrow, maybe not in 5 years, but 20 years down the road, we want to make that game change. We want to be able to innovate, whether it's in nuclear, whether it's in solar, or whether it's in biofuels. We want to make the discoveries, the fundamental discoveries that will ultimately impact. And that's what I mean by mission-driven. Of course, we have, at Argonne, we have over 1,000 PhD researchers, smaller probably than the number of engineers that you have here, but still all working in force in science to deliver that mission. We do a lot of cross-disciplinary work. So another thing that distinguishes us from, for example, a university is that we aren't PI, only PI driven. Like you guys, we've got a lot of meeting rooms, we have a lot of people working together. So we have material scientists working with computer scientists, working with chemists, and working with engineers, because we also have a lot of engineering, to try to solve some of these problems. It's somewhat different. There's a different imperative at a place like Argonne than there is, say, at a university. We have major facilities, and I'll come back to this later. Kinds of facilities we have include synchrotrons, major accelerators that allow us to study materials and chemistries at the nanoscale that you don't have anywhere else. They're open user facilities. You have one down the road at Stanford, which you can go and you could use a free electron laser to do materials science, for example, with very, very, very high resolution. And then we have research networks. So one of the things we're looking to do, one of the reasons I'm happy to be here today, is to talk about our networks. We work very hard, and not in an insular way. We're working hard with industry, we're working hard with certainly regional universities, but our collaborations, we have people coming to the lab from every state in the country and internationally as well. So we have a very large set of networks that we rely on to solve some of these bigger problems. So we could probably sit here all day and brainstorm and say, well, what would be game changers in energy? These are a list of a few that I put down last night. Room temperature superconductors, I'll come back to this. If we had a metal that conducted electricity without any loss at room temperature, you'd have a perfect transmission line, for example. And I'll come back to this one. If you could create a 1 penny per mile battery, today we're talking about something that's almost 100 times more expensive. So that's why the Volt is a great automobile, but it's got a 15 kilowatt battery in that car costs $15,000. It's a large fraction of the cost of the car. It's also a large fraction of the weight of the car. So 1 cent per mile batteries is a game changer. 5 cent a kilowatt hour solar, today it's cheapest 20 cents, and that's subsidized. So it's really 50 cents to $1 per kilowatt hour. Compared to, for example, what I pay at Argonne for electricity to power my big machines, I pay 5 cents a kilowatt hour. So it's got to compete to be fully adopted, unless you want to subsidize it, which is something California has tried. It really have to get to make something transformational, you have to be at the 5 cent level. Internet-like power grid, of course, people talk about all the time. If you have solar and wind and nuclear is a constant, solar is very variable, wind is very variable. You really like to manage the country's energy grid like you manage the internet. The country is broken into 3 grids. There's the West Coast, there's the West grid, there's the East grid, and then there's Texas, believe it or not. But even within those grids, it's broken up. If you go to the southern part of Illinois and look over the border of Kentucky, you'll see a 110-volt line running across from someone's backyard to another backyard. You can't possibly share power. And in fact, that means in Illinois, where we had a lot of nuclear, we have a glut of power. That's why I can pay so little for it, and why here you're paying a little bit more than I'm paying. You're getting it from a little bit farther away. But the point is, if you could manage the grid like the internet, if you really could, you'd have a modern grid, and you could add all these renewables to it. And the last I mentioned here, we can debate, but fuels, this is sort of fuels from sunlight. It's actually a project that Caltech and Berkeley are working very hard on now, but it's a great idea. The idea that we want to mimic a photosynthesis. We want to take CO2, H2O, very simple molecules, and with a photon from the sun, produce alcohols, sugars, alcohols, ultimately even sophisticated drop-in biofuels like biodiesel. If you could do that at scale, you'd have something important, and we could debate whether you can do that or not. So what I thought I would do is start with just an example of some of the stuff we do, but I think also reflects on what I think of as game-changing, trying to change the game anyway. And that's really thinking about 21st century transportation. The U.S., just for some more numbers, the U.S. consumes about 20 million barrels of oil a day, okay? If you could wean all of our transportation from using petroleum, using gasoline, to electrifying it, meaning you go from filling a gas tank to powering your vehicle with a cord. We've estimated, these are numbers, and I'll talk about those in a minute, we've estimated that you'd reduce the consumption of oil by 1/3. That's about 7 million barrels a day. That's a huge change. So if you're talking about energy independence, that's a good move. It's a good thing to do. At the same time, because so much of the carbon produced comes from automobiles, you save about 25% of the carbon we produce. So both really good things. We did this, we actually have what we call life cycle analysis at Argonne, and we've done this for the country. We've also done it for China. So when we do this for the United States, we reduce the carbon footprint by 25%. You could ask the same thing about China, and this is an interesting point. If you take China and ask, well, let's say we electrify, and they have goals now to reach 10 million by 2025, 10 million electric vehicles, and ask, Does that reduce the carbon footprint? The answer is no. It turns out because China is 80% coal-powered plants, just by shifting the power generation back to the power plants, you can say, oh, you assume because you have a battery-operated car you're doing better. You don't. But in this country you do, because 20% of our electricity is nuclear. There's a large fraction that's natural gas, 10% is natural gas. There is a lot of coal, there is a lot of fossil fuel in there, but the point is that you have to ask the question. It's a systemic question at the system level, and if you don't ask that question, you can't just assume, well, doing electric cars is a good thing. So we think it's a good thing because, of course, in the US, we could have a significant impact on energy independence and on carbon footprint. What is one of the major challenges, and this is really where Argonne spends a lot of its time, is thinking about how to store energy in compact spaces. And this is really a chart just meant to give you a sense of where we are today, but where we need to be. This is a funny chart. It's theoretical versus practical specific energy. Specific energy is just the amount of energy I can pack per kilogram of battery, okay? So just as a reference, I have octane, gasoline. Gasoline, we're way far away from gasoline today, okay? And gasoline, so if I want to power a car 400 miles, right? If I want to move a car 400 miles on a single charge, for example, with an electric car, today, because I'm using lithium ion at best, I need a battery that's 10 times the mass of gasoline that I put in my tank. So that's why if you look at the Chevy Volt, which I showed on the last slide actually, I'll go back to that. If you look at the battery in the Chevy Volt, it's this massive thing that fits underneath the car that weighs actually more than 500 pounds. And that gets you about 40 miles. You want a factor of 10, the battery has to be 10 times bigger, and this is the reason. You just can't get enough energy per kilogram. So what we're doing is thinking about what's next. So batteries are here, lithium ion, that's what we all know, and all the things you hear in the press today about lithium ion, if we do great stuff, and we are going to do great stuff, we get a factor of 2 in energy density. See, the dot is actually theoretical limit, where we're sort of at the bottom of that red oval. So we get a factor of 2 if we push really hard, which means that the technology has to change. You can't use lithium ion to do what we really want to do. And Americans in particular, in China, if you're driving around Beijing, you might get away with a 40-mile vehicle. But in this country, in California, certainly in the Midwest, you're not going to get away with a 50-mile vehicle won't do it. You need a 400-mile vehicle. To do that, you need to go to these brand new technologies, which I'll talk about in a minute. Lithium air, lithium sulfur, a new way to think about a battery. It's actually a battery that breathes oxygen and is able to get much higher energy densities. There is, by the way, from a physicist's point of view, and I'm a physicist, a lot of room at the top. Even if I look at octane, hydrogen bonds and octane are what store the energy, and when we burn them, that's what we break. You get a lot of energy out of octane, but octane isn't the theoretical limit. The theoretical limit on paper is about a factor of 100 greater than today's batteries, and maybe a factor of 10 greater than even the dream I have up here to replace gasoline. And it's actually getting down to quantum devices, which I won't talk about, but from a physicist's point of view, there's a lot of room, a lot of headroom, meaning a lot of cool research, which is what we're about. So just wanted to point that out. So here's just an example of a future battery. This is a battery that, if we could build it, we haven't built it yet. I would call this a known unknown, because we don't know how to do it yet, but we know that if we could build this kind of battery, we could get to the energy densities that would get you that 400-mile vehicle. I won't go through the details, but it involves a different way to think about batteries. Always look this way. There's a cathode and there's an anode, and the anode and cathode are differently charged, and then lithium and a lithium-ion battery shuttle back and forth, usually through a liquid. When you charge it up, the lithium go over to this cathode, and when you discharge it, the lithium filter back into the anode. When you charge it back up, like in a lithium battery, you drive the lithium back over onto the cathode side. And that's how battery cycles. It's very simple. This is an advanced idea that we're working on, which involves different kinds of cathodes and anodes. But fundamentally, it breathes. And it breathes because it takes the lithium ion and combines it with oxygen and makes lithium peroxide. The challenge there, it's great because actually you get a lot of energy out of that bond, so you can get it out of the battery. The problem is breaking it up apart. That's why we need catalysts to break lithium oxide and oxide-oxide bonds. But if you made a battery like this, the reason it's called lithium air is it actually breathes. The oxygen comes in, burns the lithium, and then goes back out again. You have to be able to get it to come back out again. And by the way, that problem is a chemistry problem. Lithium oxide, breaking lithium oxide, it's the same chemistry problem or similar to the one I need to make CO2, H2O, and sunlight into sugar. So there's a lot of commonality in the fundamental science we have to solve to make these kinds of exciting things happen. So this will give you the energy density. Just one other example is nanoscience, and you guys I know have heard about nanoscience. This is just a nanoscience example. This is not for energy density, although it gets high energy density. Using nano, you can actually do fast charging. So one of the other problems when you think about range anxiety is if it takes 8 hours to charge your car and you can only go 30 miles, what do you do when you get to work and how do you get home? We have to think very differently about how to structure the batteries. And this is a way to think about it. You have to have a lot of porous material that are dense. And so it turns out you can use things like this, which is using a patterned array of these titanium oxide tubes. The tubes are hollow, the lithium can get in and out, it can do all kinds of things. So you can actually do clever things, and we're starting to think about using nanotechnology also to drive the speed and the density. So you're combining these things. So this is just one example. I'm talking about energy density, I'm talking about speed of charging. But in the end, right, this is what we want. We want to replace the leaf, right? I mean, it's green, it's got everything you want. And creating an artificial leaf would really be a dream. Today, if you look at a leaf, this is green, right? So as my friend Nate Lewis at Caltech would tell you, if a leaf were really efficient at absorbing sunlight, it would be black. The fact is that a leaf is not very efficient at taking sunlight and converting it to sugars, which provide it with life. It's not efficient because it doesn't need to be. It's really interested in reproduction. It's not interested in producing at scale lots of material, lots of, say, ethanol that we would like to have. So we're working, and a lot of people are working on the idea of really taking a leaf. But there are many other problems like this, but taking a leaf and making fuels, learning how it works, learning how proteins work, et cetera. So this is a very interesting problem, but it's yet to be solved. One other point I'll make is just in case you have a conversation at a cocktail party about biofuels, because you all hear about it, I want to make one point. Solar energy, on the average solar influx or flux on the surface of the Earth is about 200 watts per square meter. So if you take a square meter and you ask how much sunlight do you get about 4 or 5 light bulbs, good light bulbs, right? And that's actually a lot. It turns out that if I want all the electricity the US uses, it's about 3 terawatts. If I took a state of Kansas, there's no one from Kansas here, I hope. If I just took Kansas and I plastered it with solar photovoltaics, I'd have enough electricity for the whole country if I could convert it at roughly 50% efficiency. The problem with the leaf, and even all the biofuels that you hear about, is the efficient. If I take that same square meter and I take the meter and let's say I go grass, and then I want to convert that grass to biofuels, like switchgrass or cellulosic materials, and I want to convert that to fuel and then burn that, how much energy do I get? Remember, this thing is only about 0.1% efficient at converting that energy. So I'm only using about 0.1% of that 200 watts per meter squared. So if you ask me as a physicist, I'd say you're much better off with photovoltaics than biofuels. The problem with photovoltaics, of course, is you have to store the power because it's automatically used. And that gets back to the smart grid. If you can bring it into the grid right away, either by storing it in big batteries or by actually using it, power generated in Southern California, using it in places like Nevada, or maybe Nevada has their own, but sending it up to Seattle, that would be a dream. So this is if you look at solar, I think in the end it's the answer, but we're far away from it because we just don't have the solutions yet. So now I'd like to talk a little bit about game changing. This is where I get into my perspective as a condensed matter of materials physicist, where the game change in the technology begins. Everything I've told you about, whether it's a leaf or whether it's a battery, involves fundamental materials, new materials. And I've already shown you that the CCD, the charge couple device, really just involved silicon. So let me start off by reminding you what really started the revolution that everyone in this room lives on, which is of course, Moore's law for silicon technology. The idea that we all know Moore's law, right? Doubling every few years of the density of chips, and it keeps going on, and that's great. But you got to understand that before we even got to the first 1K of a processor, or the 404. I personally remember the 8086. That's how old I am. I remember the first in college. That was what I had. But that's been a metronome only because we understood silicon at its deepest level. We understood silicon way back, even before 1960. We understood what silicon was like. We understood its properties, its electronic properties. We understood its optical properties, and we understood its very fundamental science. So we were able to then, with great predictability, take the risk of building a $1 billion manufacturing plant. Intel could do it, right? And easily just say, well, we'll invest the $1 billion because we know where we're going to be in 10 years. We know exactly where we're going to be. Moore's law is, of course, not a law. It's a conjecture. But the fact is we knew a lot about the material. The problem with most of the other things that I've been talking about, all the energy stuff, is that we don't know what the answer is. The materials are more complicated than silicon. The systems are much more complicated than a transistor built on silicon. And so what I have in this little patch, I apologize, it's pretty cryptic, but it shows a roadmap for batteries. And we're right down here today. We're with lithium metal oxide anodes and graphite anodes. So there'd be an anode and a cathode. And this shows you, by the time you get out to about 2019, we don't even know what kinds of anodes you're going to get based on the kinds of energy densities that roadmap projects. So I told you we have to get up that toward gasoline. We're talking about 2019 and 2021 getting closer to gasoline, but we don't even know what the materials are going to be. So if you want me to go out and say, I have an answer for you, it's going to be very hard for anyone a company to say, fine, we'll build a manufacturing plant at $100, $200, $300 million before we even know the materials. So the real challenge today in energy at the very fundamental level is understanding the materials we have, understanding how to make and how to predict materials that we can use to do the kinds of things I've been talking about, to generate a battery that's got 400 miles behind it. And so the way we know how to do that, in fact, we know. This is actually, I just got this 2 days ago. I don't know if you guys know Bob Laughlin. So he's a colleague up at Stanford University. He won a Nobel Prize for something called the fractional quantum Hall effect, but he's a condensed matter physics. This equation here, H, which is called the Hamiltonian, is really the equation of everything. If I could solve this equation, I would know everything I need to know about a material. And he just wrote this down on paper before he gave his Nobel lecture. I mean, I'm not going to solve this equation for you, and I know that solving equations is always risky at giving a talk. And I'm just showing it to tell you that, in principle, I can write down the equation that will tell me everything about the electrons and the atoms in any solid, including in your body. So the proteins in your body, life itself. And you can see the list he made. You know, if we could solve this equation, then we would know everything from how to put together an economist, which he kind of said as a joke, all the way back to Ebola virus, glass, wood, and batteries. You can do everything. And all this is, the first two terms, I'll just tell you quickly, the first term is just the kinetic energy of the electrons. The second is the kinetic energy of the nuclei. The third term is the interaction between the electrons and the nuclei. And the fourth and fifth terms are the interactions between electrons, respectively, and the nuclei, respectively. If you have that, you have everything in a solid, whether it's a protein, whether it's a protein in a leaf that's doing catalysis, or whether it's a Ebola virus. You know everything about that material. The problem is we just can't solve this equation. We can't solve it even for silicon. So for silicon, if you ask what are its optical properties, this won't help you give you that answer because you can't solve this equation. And the reason you can't solve it is it's a very complicated many-body problem. But things are starting to change, and that's one of the reasons I'm excited about it. Computing is actually slowly becoming, computing has always been important for us because we model stuff. You go out and you measure something and you model stuff. So physicists and chemists and scientists, you guys, you take data, you can model it. And it's always been possible to model. But what we haven't ever been able to really model are the properties of materials because of the complexity of that simple-looking equation. But we're actually really at a transition point now. We're at a petaflop in terms of computing speed. So we're just starting to be able to taste the ability to do things that we never were able to do before. We're not there yet, but we're getting close to it. So this is the K computer. You guys may have heard they just pulled ahead last week as the fastest computer in the world. For the last 3 computers, they haven't been here. They've been overseas, unfortunately. 2 in China, and now this third one, 1 in China, then 2 in Japan. This one is Japan, the K computer. It's a 10 petaflop machine. And of course, what we're pushing toward is the exascale. At 10 petaflops, we can actually start thinking about taking the equation and actually modeling real materials, understanding the properties of those real materials, ultimately to predict the properties of materials. So I might be able to tell a manufacturer one day, I'll tell you exactly what materials you can build. If you want to build a battery that's got a 400-mile range, here are the materials you need. So it's what I call materials by design, and I'll come back to that. But there's some challenges here. At first, you're still solving a many-body problem. And when you talk about these parallel computers, there are problems you can solve today, especially local problems, like hydrodynamics. So for example, one of the things we're using these major computers for now, Boeing uses them, for example, to eliminate wind tunnels. You can do things like hydrodynamics, you can do wind dynamics. So you can actually design an airplane. In fact, the 787 is entirely designed using computers like this at Boeing. That's great. But still, those are fairly local problems. When you get to problems like climate, which is very multi-scale and very complex, or a solid, take just a hunk of material like lithium oxide, we still can't do it with this computer. So that's one challenge. We're still working on that. We're getting closer. The other is, these computers are pretty energy intensive, so there's actually buried underneath these fast computers is also the energy challenge. Physicists always thought of the challenge with computing as being the transistor itself. And as you get to higher and higher densities of chips, you get to fewer and fewer electrons per switch. And when you get down to 1 electron per switch, it's quantum mechanical. So you switch it, and it's either on or off. That's not good enough. So that's the problem we thought was the problem. The real problem today is heat. Each of those transistors leaks. Each of those transistors has leakage current. Turns out this machine, well, 1 petaflop machine is about a megawatt of power. A 10 petaflop machine is about 3 or 4 megawatts of power. And we want to go to an exascale 1,000 times faster. So we're talking about a small nuclear power plant to power an exascale computer. So we think these will solve the problems, but we have problems to solve within the computers themselves, which is pretty cool. So let me finish by saying on this particular topic, which is to say we are making inroads on being able to take that kind of machine and compute properties and predict properties, right, which for the first time really ever in the last few years, because once we get to a petaflop, we can take that equation and solve it on a computer. It's hard to solve analytically, but you could solve it on a computer. And that's what we're starting to be able to do. And this is just some work that was done actually by Garrett Cedar at MIT. We work closely with him. And he's doing things like taking that Hamiltonian, that complicated or somewhat complicated equation, and solving it on a computer. And what we're able to do now is, instead of trying lots and lots of Edisonian approaches to materials, and that's what we do with batteries, for example. We try intelligently. We use high power thinking as well as high power computing. But this kind of computing will actually allow you to start narrowing down the kinds of materials. And in fact, Garrett has worked on lithium-ion batteries and predicted 2 new materials, which have been pretty good. So we're starting to be able to do it, but we're still probably a few years off from being able to really solve the major problems. And one of the reasons, just to give you a sense of why it's so hard, not just showing you a fancy physics equation, is to think this is just a material you may have heard of, high-temperature superconductor. And its constituents are yttrium, barium, and copper, which if you just pick them up, they're normal, boring metals. But if you put them together in a very interesting form, which essentially is made up of planes of coppers and oxygens, I have to add oxygen, which I didn't put up there, and then separate those planes basically by barium and yttrium, you end up with things that superconduct. And I mentioned superconductivity before as being one of those things that could really transform the grid, for example. So we could never have predicted this material. It was a bunch of guys in a laboratory, just like the first 2 in the CCD, who were playing around with materials and thought they might have something cool. And when they discovered superconductivity, it was just a eureka moment. They never thought they would get it. They got it. And in fact, this problem is still not solved. Physicists still don't understand why this stuff superconducts at 90. We now have one at about 130 degrees Kelvin even. So it's still a challenge, these fundamental materials problems. We can't predict, certainly can't predict how to make this material. Nobody could have. But even now, we don't understand in hindsight how this material was made. But I'll come back to the energy grid. If we could solve the problem and generate a 90-degree superconductor is great because it works at liquid nitrogen temperatures, so you can still use it. Liquid nitrogen is not so expensive. And so out on Long Island, this is the Long Island Power Authority, used to be called Wilco, for those of you that know New York, actually took 3 superconducting cables with a carrying capacity of 500 megawatts. That's huge. That's about as much power as a major power station generates. In just 3 cables, they're able to generate or transmit that kind of power. So this is just a test bed. The reason you see these fat pipes is that they have to drive liquid nitrogen through them. But one day you could imagine having these kinds of things across the grid, replacing old copper with things like this that really could transform the grid in terms of losses. So there's one more point I wanted to make, which I wouldn't call it a sour point, but it really is a struggle for this kind of activity, material science. And I hope I'm getting across the point that material science is really at the heart of all these energy technologies, whether it's chemistry like catalysis, like in plants, or whether it's new materials like in batteries or superconductors. This is a chart which only goes to 2007, but it hasn't changed out to 2010 or 2011, which kind of says what the state of the US is. And if this is just, it's done in a certain way. It's by measuring publications, percentage of publications. Since 1990 or 1992. And you see the United States has fallen. In fact, we're now well behind China, because if you do extend this, you'll see China keeps going up. We're well behind China on production just of knowledge, just basic knowledge, the knowledge that feeds this kind of important technology. We're just not doing as much anymore. These are just examples. This is an example within a particular kind of field, material synthesis. But the point is that we're not doing as much. And I sort of attribute that to 2 things. One is you guys. Because a lot of kids now want to get out and do code development. They want to do algorithms. They want to do apps. They want to do fun stuff that you guys allow them to do. And that's great, because we're attracting a lot of bright, early people. I mean, I look out in the audience, for a lot of early career people here. Really, that's good. A lot of people are being drawn away. But there's another reason, too. And the other reason is that the big labs, like Bell Labs and like IBM, no longer do this stuff at all. The US used to have these big labs embedded in companies, much like you do. You're a vertically integrated company. You've got this code developer. You go all the way up to the applications from very basic code development. We don't have that in the United States anymore. So we don't have the vertically integrated companies that drive mission. And it's one of the things that the DOE labs are trying to fill a hole. So let me sort of wrap things up a little bit here. So we'll come back to this concept of how does a game change. And maybe some of you have seen this kind of chart before. This is actually from the New York Times. They haven't done one recently, so again, it's a little outdated, but it gives you a sense of what adoption of new energy technology, or just technology in general, look like. Everything from the telephone, which took 50, 80 years to adopt, to internet, which of course was adopted very quickly. The trend you notice here, of course, is you get closer and closer to modern technologies. Things go faster and faster. And the question is, what will energy technologies look like? It's my contention that we believe we can make it go very fast, but there are a lot of hurdles to get over to get there. There's a lot of materials problems to solve, and there could be eureka moments, but in the end, we can't rely on eureka moments. It really involves critical mass of people like you guys sitting around thinking through the problems, much like Boyle and Smith did back in the late 60s. And my concern on this chart is that do we have the people sitting at this part of the curve really thinking through the materials problems, the chemistry problems that we address? It used to be, and I've kind of said this already, it used to be that we did this kind of stuff at a place like Bell Labs. I spent 15 years here. I don't know if any of you have ever been to Bell Labs. It's where the C programming language is invented. That was invented in this wing over here on the left. The wing on the right, so the left wing, just so you know, it wasn't entirely integrated. The left wing here was where all the code developers and software and guys like Richie sat. The right-hand side was where all the physical scientists, where I was, of course, way before my time. You can walk down the hall, that long, called the Infinite Corridor, this whole thing. You walk down the hall and there's a little plaque. That's where the transistor was invented. That kind of place doesn't exist in material science anymore. It doesn't exist in chemistry. It doesn't exist in those fundamental technology developments in many ways anymore, aside from places like this, in this country. And so we're trying to recreate that. So once we develop those things here, we believe that we're starting to bring the national labs into play in a very big way. This is a picture of my lab. There are 17 of us, by the way, national labs. There's one at Stanford, there's one up at Berkeley. We have one outside of Chicago, associated with the University of Chicago. This is just one of the devices we use to do discovery science. This is a synchrotron, which is about 1 kilometer around, and electrons whiz around at the speed of light, and they generate X-rays, and we use those X-rays to study things like new materials for cathodes, like catalytic processes. This is a nanoscience building here where I showed you that battery of nanotubes that was developed there. So we provide these tools, and we're trying to regenerate that ecosystem where we vertically integrate, where we have people doing the fundamental science, but also in other places besides this at the laboratory. You can see Chicago in the background if you look carefully. In other places in the laboratory, which is about 1,500 acres, we have people who are doing engineering, working closely with companies like General Motors, working closely with companies like Ford and Mitsubishi to try to solve some of those challenging problems. And of course, here at Google is where we're changing the world too. Really changing, game changing. The challenge I had with Google, of course, Google X now, we've read about in the New York Times. Maybe you guys can tell me. This is the best you can do if you try to Google X. This is what you get. So I assume what you're doing at Google X is also game changing. And maybe you can tell me what's going on in there. But this is, if you Google X, you get this. But of course, that's also where the game is changing, where you put, and as I understand Google X with what the Times said, is you put people in different disciplines who aren't doing the same things together and just let them have fun. In other words, let them really try new things. Let them try to solve the problem of the battery. Just let them go do it. Give them as much latitude as they want. Or let them go solve the problem of solar energy or photovoltaics or what have you. And that's really important. And so this is my last slide. Just to repeat again, this is actually just up the road from you. This is at SLAC, National Accelerator Lab, which is if you will, it's like Argonne. We are run by the University of Chicago. This is run by Stanford University. And what you see here is the future. Well, you can't tell it. It's just a time-lapse photo at night. Is the next generation of sources for X-rays. I showed you this big ring, which was a synchrotron. This, which you can't see because it's buried underneath some of these buildings, is a LINAC, which is about 3 kilometers long, and it's the world's first X-ray laser. So you remember back in the early 60s when the laser was invented, which was also at Bell Laboratories and Columbia University, it changed the world. Lasers changed the way we communicate. They changed everything. That was a game changer. This is a new type of laser, but instead of visible light like the red lights in the pointers or green lights in the pointers, this is actually using very, very high energy light called X-rays. And its capabilities are unbelievably dramatic. And this is just up the road from you guys. So this is the kind of thing which will change the game one day, but hasn't done it yet. So I think I'll stop there and open it up for any questions.
So one of your points there was that photovoltaics had to get down to 5 cents to be competitive. But they're being competitive with an industry that's externalized a lot of its costs.
Yeah.
So there's another way to change the game.
So I would agree with you, actually. My public statement is that. But look, I fully agree with you. If you actually look, this country is a free market economy, so everything has to be driven by free market. So that number is based on a free market economy. But I think you hit on an important point. The energy industry is anything but free market. It's run by two groups. It's run by the utilities, which are regulated like crazy. So for example, your utilities or my utilities in Illinois can't raise the rates by a nickel to pay for a new grid. They can't raise the rates by a nickel to put in big solar because they are more expensive. They can't. But if they did, they would create the market. So that's one way you could do it. And the other, of course, is we're all about petroleum, and that's a cartel. So we have no control over the cartel, mostly in the Mideast. So it is a tricky game. And in fact, I was on a panel about a month ago at the Electrochemical Society, and I was asked, it's a great question, in the end, what is really the challenge to getting these energy technologies out? Is it policy or is it technology? And 3 years ago, before I became director of the lab, I easily would have said, I'm a physicist. It's technology. We've got to invent new technology. Today, I'd say a lot of it is policy. We don't have a coherent energy policy in this country. China does. So they are spending more. Even in China, they're spending more per kilowatt than I told you here. But there's policy to level the playing field. And that's, I think, your point. It isn't a level playing field for a small company trying to do solar versus the utilities. I don't think the utilities are intentionally keeping out solar. It's just they have to deliver power to you at a cost. They can't lose money, so they have to do what they have to do, and so I agree with you. That is probably one of the major issues around adopting these technologies. It's a little different than the IT revolution, in the sense that there wasn't anything competing. Right now, of course, there is something competing. It's called oil.
So I was wondering if you could also talk about the role of public perception in energy game changers too. I'm thinking of the potential of something like thorium, but then people, when they think of nuclear power, they think of meltdowns, Chernobyl, and Japan. Yeah. So how can education change the game too? Yeah,
actually, that's a very good question. In fact, I just wrote an article in the Huffington Post about this exact problem. The public perception about energy in general is not very well defined, because we haven't done a good job at talking about it. You bring up nuclear, and that's probably the hottest button there is out there, because that always brings out the best and worst in people. People are either very afraid of it because it's nuclear, don't understand it. They see the risks. Nuclear, by the way, is safer than coal. More people die every year in coal than they ever will in nuclear power. So educating people about those risks. I mean, it's only fair that the public gets to decide the risk, the cost benefit, sort of analysis, but in the end, we don't have the right information out there. It's one of the things that we've been pushing for at the lab, and I think all over the country, is a much clearer education about what these different technologies mean, what they really cost, for example, what their impact on the environment really is, what nuclear's real impact is a good question. It's very easy to dig coal out of the ground, but look how many people die in coal mines every year. It sounds easy, but it's really not, and we don't hear those stories, but you'll hear about, Fukushima was a terrible accident, and we don't know yet the full extent of that accident. But even that, you could argue, worked right. I mean, for what it was, it worked okay, and not many people died. So there is a real issue about education, which we don't really think about. So I would advocate that we think about it in high schools, in K through 12. We think about incorporating it much more, and we see that. I mean, my kids, 13-year-old and a 17-year-old, they're seeing more of this in their chemistry classes. But it really needs to be a national effort to educate people on, at least so they can understand the risks involved with each of these technologies.
Speaking of education, I do a lot of education work, and you mentioned Google people are attracted to it because we attract a lot of programmers, developers, people who want to develop apps, and a critical part of that is the barrier of entry is very low when it comes to doing computer programming. I mean, my 8-year-old cousin is writing his first computer program right now.
Right.
Material science is a little different.
Yeah.
Is there any way to really bring material science into a classroom or create small hands-on kits that really get people involved?
When I grew up, everyone had chemistry kits. My kids never had a chemistry kit. I probably could have bought them one. But there's risks. There you go. No. You can't buy one anymore. Okay. So I think that basically it's not just because it's easier. There is a lower barrier. It's also because we don't talk about it. But also, frankly, industry isn't here anymore. I mean, I have graduate students in physics. And you see that the culture in physics has even changed since I was a grad student at MIT many years ago. Then everyone were going into it partially to be physicists, but also they realized they could go to Intel, they could go to IBM, they could go to Bell. I went to Bell Labs. I mean, that was my dream since I was 15, 17, whatever. So part of it was just me because I had that. But I think a lot of people don't hear about these things so much anymore, and all we hear about are apps, and all we hear about it. That's not a bad thing. I look at the University of Chicago. Has this great new entrepreneurial center built by Michael Polsky. And Michael Polsky is a wind entrepreneur. He actually built wind companies out of Chicago. He's made a fair amount of money doing it. And he contributed some money to the University of Chicago. In their first 5 years or 4 years of existence, they raised $130 million. Now, around here, that's nothing, but in Chicago, it's a big deal. $130 million of startup funds out of the Chicago and Bay Area. All of them, every single one of them, was for apps, different kinds of apps. So the kids are really excited by entrepreneurship, but what they're trying to do is at the low, as you say, low barrier. Look at the big companies in Chicago: Groupon, StubHub, Grubhub. Sorry, these are all companies that came out of the same kind of milieu. It's not a bad thing. I'm not speaking against that. The question is how do we excite those other group of kids? So if you look at university graduate departments today, they're probably 50% foreign, Chinese, Indian. And these days, everyone's going back to China. Not as much India, but India also. People are going home. There are a lot of great opportunities at home, and there's nothing wrong with that either. But we're not exciting our young kids in ways. So whether it's chemistry sets or just better educational programs, I think we need to do that, and we don't do that very much.
Hi, I'm going to ask a complimentary question to the last one. I was at JBay until a couple months ago, and I saw 10 postdocs there for every job that there was to be had once you finish your postdoc.
Yeah.
What can we do with our flood of postdocs to turn them into productive researchers?
Send them to us. That gets back to, it is a complementary to that, because again, I'm not going to complain here. I'm going to make an observation, and it is a true observation. We don't make the high-end stuff so much anymore, even the middle-end stuff in this country, because it's cheaper to do it elsewhere. We think it's cheaper to do it elsewhere. It's not always. So, what would you tell your postdoc if they wanted to, they choose to go into, manufacturing, say, working on an assembly line, or actually working on an Intel line, for example, in China versus staying here and working at Google, right? So it's very hard to convince people when we don't do stuff, we don't make stuff in this country. So there's one path that says, well, we'll only own the high-end IP, and we'll never actually make stuff ever again. And so people will say, well, we've given up manufacturing, so you're never going to get that same. The 9 postdocs that don't take the job at JBay will end up at, won't end up doing stuff here. They'll end up either teaching or they'll go into this business. And that's a problem. But if we don't make stuff, if we don't have a large set of jobs out there which are associated with the physical sciences, the stuff I'm talking about, materials, then I would also argue that you wouldn't. There is a move afoot to try to recapture some manufacturing. Whether we should be doing that or not is a political question. I can give you my opinion, which is we have to. But if you talk to, half of Congress now doesn't believe that at all. Maybe 51% of Congress doesn't believe that at all. That restarting manufacturing here, advanced manufacturing, I'm not talking about, sweatshops and clothing. I'm talking about high-end stuff like even beyond batteries, right? The solar photovoltaics. If you talk to AMAT, Applied Materials, just down the road here, they're building all of their plants are now in China, in Asia, Singapore, China. So we're not making stuff. And if we're not going to make that high-end stuff, if we seed that, then I have a hard time saying what do those 9 postdocs who don't get jobs at Caltech or Berkeley do. So.
Just back to the slide that you were looking at on the superconducting properties and what's out there a few generations away.
Yeah.
What are some of the other properties you're looking for in those solid materials other than like superconductivity and then battery storage capability?
That's a good question. So one I mentioned, which I didn't articulate very much, was you want to actually more on the biology side of materials. You want to learn how to. This is something that JBay does actually. You want to learn how to co-opt. For example, take algae. Algae is very intelligent at chewing grass, processing in its gut through digestion, enzymes, proteins basically in the gut, and creating things like fuels. And so actually, Jay Kiesling and his friends at JBay, you can probably talk about this as well as I, have been very clever. The problem with that, let me give you the example. If you take algae and you let it, and you can genetically engineer it, you know how to do that. We know how to do that, genetically engineer it. It's still materials, but it's biology, biomaterials. You genetically engineer the thing so it produces, let's say, ethanol, or even a higher, more sophisticated version, closer to a biofuel like a diesel. The problem is that typically that algae dies because it's like sitting in ethanol that kills life. So what JBay's been able to do, maybe you did this, I don't know, was able to engineer that algae so it doesn't die. It can keep excreting that stuff and live in that environment long enough that it can start thinking about producing more of it. So that's one thing that would be great, to either co-opt the algae, but of course in the end, I said before that it still requires sunlight, and you need huge algae ponds to do it, and whether we have the area to do it is actually the real question. The real challenge is, can you make chemistries that mimic life, that mimic that algae, that can do the catalysis in a beaker, not in an algae farm? And I don't know whether you have an opinion. My opinion is you need to do that. One day you need to co-opt it from a chemical point of view, so you can scale it. So a place like the large chemical companies like Dow, DuPont, or Archer Daniels Midland can take very, very dense cellulosic material and ultimately make into some. So that's one example. Photovoltaics are another example. I mean, the efficiency of today's photovoltaics, the best, are about 7-8%. And you need 20, 30, even 40% to make them useful. And to do that, we're not going to be able to use just a hunk of silicon. Silicon is actually not very good for optics. And then the other semiconductors like gallium arsenide are too expensive. So you need to come up with some kind of interesting multi-dimensional nanomaterial that can absorb the sunlight very, very efficiently, so it's black and not green like a leaf, and then convert that sunlight into an electron in a hole, and then basically charge a battery with it, or send it out onto the grid. And we don't have that material yet. We don't have a material that can do that in a big way. What else? I mean, I can go on and on, but these are just examples. Everything that I can tell you. Even take nuclear energy, actually. We're at the end of life. We have 104 reactors in this country. And the last one that was built was somewhat just before 3 Mile Island occurred. We haven't built one since then. So look, they're all at least 40 years old, and some of them are 60 years old, 55 anyway. So we're extending their life. The materials in those containment vessels are embrittled. We have to learn a lot about how to make materials that withstand defects that are induced by neutrons, for example. So there are a lot of good problems to solve for the right reasons. We're only working on some of them, not on all of them. We're getting beat out. I kind of made that point. We're kind of getting beat out by a lot of other countries now. It's not to say we still don't have the smartest guys in the world. I mean, Stanford itself, I know the physics department there has a great group of people doing this kind of work. And they're great, and they have a critical mass. But it's only one of many places. If you go to China, there's a tremendous number of activities like that. Any other questions?
How close are we to something like solar shingles, where you would just replace your regular shingles by solar shingles and grab some power?
At cost. There's actually a DOE program out there called Sunshot. And the Sunshot program, it has, I think it's by 2017 or 18, they're shooting to do that, basically. They're looking at the cost I gave you, something like 7 cents per kilowatt hour, unsubsidized. So to your point before. And so if you ask me, it's somewhere between 2017 and 2050. If you were to ask me what the ideal would be, I would say we should have left Yucca Mountain open. We should have built out a couple of nuclear reactors to compensate. Instead of growing coal, which is what we're doing, we grow nuclear. And then by 2050, we'll solve the solar problem entirely. And we'll be able to use, the slide I dropped out of this talk, if you look at just the usable land, we have about 10,000 terawatts of sunlight. And I told you we only need about 15 terawatts on the face of the Earth today. So again, there's a lot of headroom, physicist headroom, but there's a lot of headroom. So it just seems to me we have to get to that time. I'm giving you a big range because there could be some eureka moments in the material development, and if there are, then it'll be accelerated. But that adoption curve is still, I would say, it's still probably. We'll see. Germany is actually the best producer of solar now. They have good solar panels. They're very expensive. China makes the most solar panels. They're not as good, but you could argue you could buy them today. They're still more expensive than pumping electricity in through a wire from your grid by a lot. So if you're willing to pay more, you could actually do it today. But if you want to do it at cost, it's probably 10 years, 5 to 10 years.
Well, here the electricity is 31 cents a kilowatt.
Yeah, I know. Well, here, maybe it's easier here, and that's why, for a while California had a program, well, there was a tax subsidy, right, for installing solar panels on your roof. I forget the name of the program, but it was okay. It worked for a while. I think it's no longer. I think that's probably because.
Well, what I mean is, even unsubsidized can be 31 cents.
No, what I'm saying is it's easier to make the bar here in California, right? So if you get below 31 cents, maybe you've got enough people who will adopt it. But you still have. So as an individual house, you can do it. But as California, it consumes a large fraction of the U.S.'s power. Just count the people. And so you still have a grid issue, and the question is, can you provide power in a city, for example? And I don't know that San Francisco is not the best place to have solar, right? So LA is probably better. So you could subsidize the amount of electricity you use, but you're not going to ever be grid-free. You're not going to be off the grid, I think, in California. Some houses can be, obviously, but on average, it's not going to happen. So, any other questions? Well, thanks, everybody, for listening.